Welcome to my talk on stochastic dueling bandits with adversarial corruptions. Dueling bandits is an extension of the classical bandit framework motivated by practical settings where it's difficult to elicit absolute feedback but possible to get relative feedback. In this setting, there's a set of k arms, and for every pair of arm I, j, there exists an unknown probability mu ij of arm I beating arm j. You can alternatively view these parameters as a preference matrix over probabilities over pairs of arms. In each round T, the player gets to select a pair of arms IT, JT to play and observes the outcome of a comparison between IT and JT, which is Bernoulli with parameter mu IT JT. Typically, a lot of assumptions are made on the structure of the preference matrix. We only assume the existence of a Condorcet winner in mu, which is a unique arm I star that beats every other arm with probability strictly more than half. The objective is to minimize the cumulative regret over a fixed time horizon T. The regret is defined as the sum over all time steps T, delta IT plus delta JT, where delta J is the gap of arm J, which is mu I star J minus half, and it's intuitively the advantage of arm I star over arm J. So why do we need to be robust? There are two reasons really. Firstly, dueling bandit algorithms are useful in several online applications such as online rankers and recommendation systems. So there's a natural incentive for malicious players to provide adversarial feedback to influence the rankings or recommendations of certain products. Secondly, assuming that the observed feedback is always stochastic according to an underlying preference matrix is too optimistic for practical settings. What if the received feedback occasionally deviates from the underlying model? Unfortunately, existing algorithms for dueling bandits do not work in this setting. In fact, we show that some standard algorithms necessarily incur linear regret in the presence of even marginal amounts of adversarial feedback. The question is, can we design a provably robust algorithm for dueling bandits when some of the received feedback may be adversarial? What we desire is, firstly, the regret should degrade gracefully with the amount of corruption in the feedback. And secondly, we should not assume any prior knowledge of the amount of corruption that will be received over the time horizon. This setting has gained a lot of attention in the classical bandits community. See, for example, Likouris et al. And Gupta et al. The contamination model that we study is an extension of the model studied in the classical bandit setting to the dueling bandit setting. There's no prior work on this model in the dueling bandit setting, though. So our contributions are threefold. Firstly, we provide a powerful adversarial contamination model for this problem. In particular, we allow the adversary to be fully adaptive. And we prove that some standard algorithms are extremely vulnerable in this framework. We present an asymptotically optimal algorithm under this framework whose regret scales additively with the realized amount of corruption across the entire time horizon. And it does not require knowledge of the amount of corruption that will be received ahead of time. We also show that such an additive dependence on corruption is necessary. So what's our model? The instance consists of a set of k arms and an unknown preference matrix mu, such that mu contains a Condorcet winner I star. So for all suboptimal arms, delta J is defined to be the gap of arm J, which is mu I star J minus half. For each time step T, nature draws outcomes of comparisons between all pairs of arms, such that the outcome between I and J is Bernoulli with parameter mu ij. An adversary then observes these outcomes and reverses some of them, producing corrupted outcomes. So in the figure on the right, the cells highlighted in red are pairs for which the adversary flipped the outcomes. The adversary is allowed to be adaptive in the sense that its choice to flip pairs can depend on the realization in round T as well as the entire execution history, which includes the player's past choices. Finally, a player selects a pair of arms IT, JT to play and observes the outcome between IT and JT. The objective is to minimize the strong regret RT. The main result is as follows. There exists an algorithm for stochastic dueling bandits with adversarial corruptions whose regret with any constant high probability is at most the following, where k is the number of arms, I star is the Condorcet winner arm, t is the length of the time horizon. For any suboptimal arm j, delta j is defined to be mu I star j minus half. It's the advantage of the Condorcet winner arm I star over arm j in the pairwise preferences mu. Delta min is the minimum of all of these quantities. And C I star is the total number of pairs whose outcomes were reversed by the adversary across the entire time horizon, where one arm of the pair is I star. So let's look at this a bit more carefully. So the corruption-dependent term, our algorithm does not assume any knowledge of the amount of corruption ahead of time. And it's a weak dependence on corruption in the sense that it's additive and it's completely independent of the corruption that's introduced into pairs of strictly suboptimal arms. The corruption-independent terms are comparable to some of the best-known bounds achieved in the completely stochastic setting. And when there is no corruption incident on the Condorcet winner arm, we can recover an asymptotically optimal bound that's achieved in the usual stochastic setting. Our algorithm borrows ideas from the Barbar algorithm of Gupta et al. For the classical multi-arm bandits. It's based on the following two principles. Firstly, no arm is eliminated completely, which ensures that the adversary cannot simply force the Condorcet winner arm to get eliminated early on, which would incur linear regret in the subsequent rounds. And arms played in any round are randomized, so that ensures that the adversary needs to corrupt a lot of pairs in order for the player to observe corrupted feedback. However, there's a key difference from classical bandits. In classical bandits, there is always a linear ordering over arms imposed by the mean rewards mu. In dueling bandits, you know that I star is better than all other arms, but in general, there's no ordering over the suboptimal arms. So that implies that in classical bandits, exploration, though it incurs regret, it always provides useful information to distinguish suboptimal arms from the best arm. Whereas in dueling bandits, if you play pairs that do not involve the Condorcet winner arm, it would incur regret without providing any real meaningful information for the identification of the Condorcet winner. So quickly isolating the winner arm while allowing for adversarial corruption in addition to sampling noise becomes a crucial challenge in our setting. So our algorithm chooses to play the following arms. So at all times t, it maintains a candidate Condorcet winner arm Vt called the anchor arm. This arm is deterministically played in round t. The arm that's played against the anchor arm Ut, which is called the left arm, that's randomized. The anchor arm is aggressively replaced. So if across the entire execution history, it is observed that the left arm Ut beat the anchor arm Vt a majority of the times, then the left arm Ut becomes the new anchor arm for the next round. Intuitively, the optimal sampling rate for any suboptimal arm as the left arm should be roughly proportional to 1 over its gap squared. So the idea is, supposing the anchor arm was mostly correct, then the fraction of times J was beaten when it was played as the left arm is an estimate for half plus delta J. But there are two sources of error in this estimation. Firstly is adversarial corruption in feedback, and secondly, we have feedback from rounds where the anchor was not I star. So how do you estimate delta J? At a high level, our algorithm divides the time horizon into epochs of geometrically increasing length. So there are log t epochs in total. At the end of every epoch, we compute delta Jm, which is an estimate of the gap delta J using samples that were collected only in epoch m. This geometric nature controls the long-term damage caused due to corrupted feedback. First of all, delta J is estimated to a precision of only 2 to the minus m in epoch m, which is what gives us this geometric nature of the epochs. And it is roughly equal to a lower confidence on the average disadvantage of arm J when J was played as the left arm. Its exact calculation depends on whether one of the following two events occurred. So firstly, if there was an arm I that remained the anchor for over half of epoch m, then it is estimated to be a lower confidence on the average disadvantage of arm J when J was played as the left arm and the anchor was I. If there was no such anchor, majority anchor, then it is the average disadvantage of arm J when it was played as the left arm in general. The former represents a scenario of high certainty where the algorithm believes with high confidence that I is I star. Second case, there is no clear winner per se, and it's the average performance of J against an aggregate anchor. So these estimates determine the sampling probabilities in the subsequent epoch. Specifically for every round T in the subsequent epoch m+1, J is sampled as the left arm Ut with probability inversely proportional to its estimated gap squared. The proof can be the regret can be broken down into regret due to playing each suboptimal arm J. So it effectively reduces to bounding the error in estimating delta J in each epoch m. So we can show with some careful martingale analysis that with high probability for all arms J and all epochs m, the estimate delta Jm is roughly equal to the true gap delta J plus minus these two sources of error. Here Nm is the length of the epoch m. C I star Jm is the number of corruptions in pair I star J in epoch m. And Dm is the number of times I star is not the anchor arm in epoch m. So the former is the fraction of times the adversary corrupted the outcomes of the pair I star J in epoch m. The latter is the fraction of times I star was not the anchor arm in epoch m. So with some algebra, we can show that the regret is at most the sum over all epochs m, the number of times the adversary corrupted I star in epoch m, plus the sum over all epochs m, the number of times I star was not the anchor in epoch m, plus this other term that is kind of the optimal regret. The first term is easy to deal with because it can simply be charged to the adversary. The second term, observe that we can view feedback from rounds where I star was not the anchor arm as another form of adversarial error, but bounding it is not quite obvious. What helps us are the following two observations. Firstly, arm I star has a constant advantage of at least delta min when it is played against suboptimal arms. And a given amount of corruption can only distort the estimates of delta I star by a plus minus C over Nm factor. So when the epoch becomes long enough, then delta I star will be estimated correctly. What this means is that there exists this magical epoch m naught, which is roughly log of the total amount of corruption incident on arm I star divided by delta min, after which I star will be sampled with the highest probability as the left arm. Secondly, any suboptimal arm J can empirically dominate I star at most a constant number of times, which is dependent on the total amount of corruption in the pair I star J and the model parameters delta J. Therefore, the total number of times that arm I star gets replaced by the anchor by a suboptimal arm or fails to replace a suboptimal arm, anchor arm when it is sampled as the left arm is bounded by a constant that's dependent on the total amount of corruption incident on arm I star and the model parameters delta J. So what this means is that the total number of times that arm I star will not be the anchor arm after epoch m naught is bounded by a constant. Finishing up is easy. You simply decompose the regret into regret prior to epoch m naught and regret after epoch m naught. The first one is at most the number of rounds in the first m naught epochs, which is at most C I star divided by delta min. The latter, if you recall the result from 2 slides ago, we simply substitute the bound on the number of times I star was not the anchor arm after epoch m naught, which gives us our final bound. So the epoch m naught after which the algorithm incurs low regret depends on the parameters of the underlying instance as well as the amount of corruption added. However, the algorithm assumes no knowledge of this and is completely oblivious to this transition. In conclusion, we study the stochastic dueling bandits problem under a condorcet winner assumption on the preference matrix, where we allow some of the received feedback to be adversarial. We propose a powerful contamination model for this problem, where a fully adaptive adversary can corrupt some of the feedback. A similar model has been studied for classical stochastic bandits. In this model, we design a robust algorithm that incurs asymptotically optimal regret guarantees that assumes no knowledge of the amount of corruption that will be observed ahead of time. So regret depends additively on the realized amount of corruption incident on the condorcet winner arm only. We show that such an additive dependence is also necessary, but it was excluded from this talk for time constraints. We encourage the interested viewer to refer to our main paper for additional details. Thank you.